Okay, let's recap what we learned last time about exponential functions. Everything we know about exponential functions starts out from saying the percentage growth rate is constant. What I want to do is just make it a little example where the growth rate is constant and we have a starting value. So let's say that Q equals 150. They usually use Q or P when they're using exponential functions at the beginning. They'll also say initially, which means exactly the same thing. And the growth rate say equals 2% per week. And I just want to make a table. Well, I'm going to make a table where the variable's t. I like that. And what I want to do is watch what happens to my q. At the very beginning, they say q is 150. So I'm just going to put a 0 in for t. That's at the beginning. And q is 150. Now, they said it grows 2% per week. So I'm going to let a week go by. Now, what happens? Well, we still have the 150 we had last time, but it grew 2%. And what that means is we add 2% of 150 to it. So here's 2%. Here's the 150, like that. Now, generally in algebra or arithmetic, we can simplify two ways. We can either multiply everything out, or we can factor stuff out. It turns out with exponential functions, if you factor stuff out, you'll see a pattern really, really quickly. And actually, it starts real quick. So I can take out a 150 here. So taking out a 150, what's left is 1 plus 0.02. Now, by the way, this already doesn't look linear because I didn't go from 150 and add something. I took 150 and I multiplied by something. Now, by the way, what did I multiply by? I did not multiply by the 2%. What I multiplied by was the 1 plus 0.02%. I just want to make sure this pattern keeps happening. I don't want to draw too much conclusion. After 2 weeks, what do I have? Well, we have what we had after 1 week. Looks like that, right? Plus 2% of that gets added into it. That's what we mean by growing 2%. So I'm going to take 2% of all of that. So I write down 150 times 1 plus 0.02% like this. Now, like I said, in algebra we have two options when we're simplifying things. We can either multiply everything out, but that usually destroys patterns, or we can look at our great big huge terms. We have two terms are what's separated by a plus or minus sign, and they have a ton in common. In fact, both of them have a 150 times 1 plus 0.02. So if I pull out the 150 times the 1 plus 0.02, I just want to see what's left. Well, if I take 150 times 1 plus 0.02 and I divide by 150 times 1 plus 0.02, I get 1. The plus sign is still there because we're using the distributive law. If I now take 0.02 times 150 times 1 plus 0.02 and I take out all of the 150 times 1 plus 0.02, what's left is 0.02 like that. Now, we could leave it like that, but I do see 1 plus 0.02 times 1 plus 0.02, and what we're going to get here is 150 times 1 plus 0.02 squared like that. Now, remember what we said. We said to go from the first row to the second row, we multiplied by 1 plus 0.02. We now see, by the way, that go from the first row to the second row, we multiply by 1 plus 0.02. And what changed, by the way? Just the exponent. We could do the exact same thing and put a 3 here, and what we would get by just pulling out the same terms is 150 plus times 1 plus 0.02 cubed like this. And then we have two things happening. Number one, to go from row 2 to row 3, we see that we multiplied by 1 plus 0.02, and you can see that only the exponent is changing. That they call them exponential functions because in the formula, only the exponent changes. And we can tell if something is exponential by asking ourselves, did we keep multiplying by the same thing each time? And we absolutely did. We kept multiplying by 1 plus 0.02, 1 plus 0.02, 1 plus 0.02. Notice we did not multiply by 0.02. What we multiplied by is called the growth factor, not the growth rate. Yes. Let's just write this down as a conclusion. We keep multiplying by the growth factor. And you can see that that's going to be 1 plus the growth rate each time. So if we wanted to create exponential data in the same way we created linear data in the first recap, here we go. I want to do something very similar. Let's create exponential data. The nice thing about this is we can create exponential data without actually having to work hard for a formula. What we want, again, I'm going to use t's because with exponential functions, t's is more common than x. I'm going to put a little q. I'm going to have a starting value, how about 3, and I'll keep going up by 2's each time. So 5, 7, 9. And I put any numbers I want to in here. How about 4 and 7? That was really kind of weird. But remember, with exponential functions, we keep multiplying by the same number each time. Now, the delta t's are constant. This is how we normally make functions anyways. The first column is always, the delta t's here is just constantly a 2. Exponential data is a little bit weird, right? What I want to ask myself is, instead of asking myself, what do you have to add 4 to get 7? We want to ask ourselves, what do we have to multiply by 4 by to get 7, right? And with exponential functions, we call that growth factor b. So we want to solve for b. Solve for b. Now what is b? It's the number you keep multiplying by each time. So I'm going to write down 4b equals 7, so that b equals 7/4. That's what you have to multiply 4 by to get 7. But if you want this to stay exponential, now you just have to keep multiplying by the 7/4. So this is going to be 7 times 7/4. If I multiply by 7/4 again, I'm going to get 7 times 7/4 squared. If I'm not sick of this already, I'd put an 11 there, and this should be 7 times 7/4 cubed. And you can see the patterns that we saw in the first example keep happening here. We keep multiplying by the same number each time, and eventually when we see the pattern, we can see that only the exponents of the answers are changing. Those are the two huge things about exponential data. Let's start with the growth rate.